So good day everyone, and welcome to Claranor. My name is Christophe Riedel, and together with my colleagues Xavier Aubert and Levy, we will give you a short introduction to what's known as pulsed light sterilization. We will describe worldwide trends in the sterilization industry, what pulsed light sterilization is exactly, and we will conclude with the practical, financial, and environmental advantages of working with pulsed light. During this presentation, we will ask you 2 questions with the integrated polling system, and afterwards, we'll open the discussion at length and answer your questions. We will also have a survey at the end of this webcast. Please take 1 minute to give us your feedback. You see, at this moment, the sterilization of caps, closures, and cups in a packaging line is, most of the time, a dirty job because of chemicals, because of excessive use of water and heat. But for manufacturers of dairy and beverages, there was no alternative. Well, now there is. But before we go into details, I'd like to present my colleagues. Xavier.
Hello everyone, I am Xavier Aubert. I am a research and development engineer at Claranor. I achieved my PhD in plasma physics in 2007 and now use my knowledge to improve Claranor solutions.
Hello everyone, I am Levy. I am a microbiologist and I'm doing a PhD thesis for Claranor in the Department of Microbiology at the National Institute of Food and Agricultural Research in Avignon. I am working on the factor determining the efficiency of pulse light to destroy microorganisms in the food industry.
Before speaking of pulse light solutions, let's explain what are the current trends in beverage and food industry for packaging sterilization. At this moment, a few technologies set the standards the industry has gotten accustomed to for packaging disinfection. There are chemical procedures such as hydrogen peroxide and peracetic acid, and physical methods such as continuous UV systems or irradiation techniques. These solutions have a significant impact on energy usage and produce undesirable waste products such as chemical residues. But they are what the industry has gotten used to as the norm. And though suppliers improve within these systems, the norm has never changed. We want to demonstrate that now there is an alternative, a new norm. Pulsed light can improve the quality as well as the sustainability of the sterilization process without decreasing the performance or being ridiculously expensive. Why would you want to change the norm? The understanding that we should produce materials and consumer goods with respect for the environment is not just a trend. Consumers are increasingly sensitive towards the industrial practices. In anticipation of possible pressure by consumers, politics and regulations, industries seek ways to reduce the impact they have on the environment. In this effort, packaging plays a large role. And if you change now, you own the story. It happens more and more. Companies that improve on their packaging use it to their advantage in their communication. For example, Danone compiled a marketing campaign based on reduction in packaging, and Pepsi intends to display the carbon footprint of a product on its label. It is only a matter of time before the first supplier starts printing the amount of chemicals used for sterilizing the package. Using a clean and dry packaging process is an asset, of course, because it's truly a better, a purer solution with less effects on the environment, but also because it is a good story to tell in a campaign. It's easy to understand and could tell a compelling story. let's face it, who wants chemical residue in their clean packaging?
These global trends are especially important for products that need their packaging to be disinfected before filling. These are sensitive products we can range in two categories. First, beverages packaged in non-aseptic conditions. They are partly shelf-stable as they do not contain many nutrients or contain preservatives. They can be juice-based beverages, soft drinks, drinking yogurts, flavored waters, for example. For these products, the cap can constitute a safety issue. The second category is dairy products packaged in preformed cups and preserved in cold chain. Depending on the composition of the product and on its pH, there is a risk of microbial development, molds, and bacteria. These are dairy desserts, creams, and low-acid products. To ensure the safety of those products, the solutions up to now were the use of chemical disinfectants on the packaging prior to filling, hydrogen peroxide mainly, continuous UV systems, or irradiation of packaging materials.
In recent years, more aspects of the existing technologies, the norm, so to speak, have been criticized.
Firstly, the technology is not instantly available. It takes time to start the process, either because of the preparation of the chemicals or heating the UV lamps. Secondly, the process is also difficult to reproduce and trace exactly, which makes it hard to identify improvements. Third, the amount of energy and water necessary to run a hot treatment induces a high environmental impact for chemical solutions. Fourth, when using chemicals, there is a risk of residue in the packaging. And fifth, chemicals are unhealthy for the operator and for the equipment, which degrades and erodes. Finally, the space needed to install a chemical sterilization system is considerable. Sometimes it's difficult, if not impossible, to implement it on an existing line.
We are now come to the heart of our presentation, Pulse Light Solutions by Claranor. Pulse Light is high-power light that sterilizes heat-free, pollution-free, dry, compact, and very fast-acting. This is how it works. Energy needed for product decontamination is accumulated in a capacitor. Then, a high-voltage signal initiates the so-called arc formation. An arc is highly ionized gas with strong currents. We use xenon gas because of its capacity to convert electrical energy into light energy. This arc starts a flash of intense luminosity. The peak power of one flash is around 1 megawatt. This power is obtained by dividing the electrical energy stored in the capacitor by the pulse duration. These flashes present a continuous spectrum rich in UV light that lasts a few hundred microseconds. The housing of the lamp is made of quartz, so almost no optical energy is wasted. The flashes are controlled and concentrated by aluminum reflectors, specifically designed for each application. The composition of a standard pulse light unit is as follows. The electronic bay contains the charge and discharge modules which generate the electrical pulses to ignite the lamps. The light is produced in the optical cavity. It contains the lens and reflector. The latter focuses the light from the lamps on the packaging. Lamps and reflectors are cooled by a water cooling system. And now, Caroline will tell you about the effect of pulsed light.
Pulsed light has a completely destructive effect on microorganisms thanks to a combination of two phenomena. First, the sterilizing effect of UV. The DNA in the cells of microorganisms absorb the UV rays. This ruptures double strands of DNA and provokes the formation of abnormal single-strand bonds. This prevents DNA replication. The microorganism's protein production and cell metabolism is blocked, and it dies. This effect is combined with the power of the flash. Intense energy delivered in a very short time increases this lethal effect. Pulse light has a completely destructive effect on a wide range of microorganisms, bacteria as well as molds, in either vegetative or spore forms. Validation trials are done with the industrial reference microorganisms, generally Bacillus subtilis for bacteria and Aspergillus niger for molds. You can see on the graph the pulse light efficiency on Bacillus subtilis and Aspergillus niger spores spread on a polystyrene surface. For these two microorganisms, we reach more than 5 log reduction in only one flash. And now, Xavier, can you present Claranor's know-how?
The first work in the scientific literature on the application of intense pulse light to inactivate microorganisms was published in 1990. Microbiologists could not develop the setup in a sustainable way, mainly because they didn't have the required equipment. At the same time, physicists didn't optimize this equipment and lacked the knowledge to analyze the consequences of treatment from a microbiological point of view. Claranor has managed to gather the necessary skills in microbiology, electronics, optics, and engineering, internal as well as external, to industrialize the laboratory setup and to manufacture equipment that meets industrial needs. The fundamentals of microbiology are studied in collaboration with the National Institute for Food and Agricultural Research, while microbiological validation of new industrial equipment are performed by independent laboratories such as Fraunhofer Institute in Germany. We continuously work on topics which enable us to improve our solutions, such as the optimization of the optical components with a computerized modularization of reflectors.